Here we go. I see lab reports. Thank you. I've just handed back your labs, and we talked about that already. Your submission for the water gem stuff that we did will be the Tuesday after Thanksgiving, so December 3rd. I'll collect that from you in lab, at the 2 o'clock and the 3 o'clock lab times. And then on Thursday is when that final homework assignment will be collected. Today we're going to talk about the energy equation, and we'll just have 2 lectures, which is a very quick run through the energy equation. But the good news is that there's a lot more detailed coverage of energy equation and how to handle friction losses in pipes in next semester's class, Civil Engineering 331. If any of you tried to register for that class and it was full, I've asked the Associate Dean to increase the number of seats for that. I don't know why it was set at 16. It was probably just an accident. But it should be open soon. And so anyways, we're talking about the energy equation today. And it allows us to get away from some of the limitations that we've had in calculating the forces and the pressures associated with flow movement. We've talked about different types of forces on a fluid, like the pressure forces that accumulate when a plane or a curved surface is submerged underwater. We've talked about, for example, shear stress when 2 plates are moving over each other, a shear stress, or even the shear stress of flow inside of a pipe. But when we allow ourselves to sort of acknowledge the fact that energy is lost as flow goes through a pipe by considering the energy equation, then that opens up calculations like how much power is required to move fluids from place to place, what the flow rates will be when the situation is unregulated and there's just a pipe connecting 2 reservoirs and no pump between them. We can calculate what the flow rate will be between the 2 reservoirs. And also we can calculate minor losses or energy losses that are due to bends, valves, elbows in pipes. That's what we'll be doing in the lab the week after Thanksgiving, is we'll be working with the pipe rack again, and this time measuring the pressure losses that occur at some of those fittings that you notice on the pipe rack. Now, Bernoulli's equation looks similar to the energy equation, but the energy equation takes things a step further. Here is Bernoulli's equation, and what were the 4 limitations or assumptions that we applied when we were using Bernoulli's equation? Do you remember what those were? Incompressible fluid that's inviscid, which of course means it has no viscosity, steady flow, and along a streamline. So those were the 4 conditions that are supposed to be met to apply Bernoulli's equation. And we know that those conditions are never met, because a fluid that has no viscosity doesn't exist, but those fluids that have very, very low viscosity, like gases, are compressible. And what we're trying to have is a fluid that's incompressible. Maybe water comes close, but then water has viscosity. And so there really is no perfect fluid that will apply entirely with Bernoulli's. And so when can we apply Bernoulli's equation with confidence? There are some places that we can apply Bernoulli's and it works pretty well, and others when we really shouldn't be applying it. From a practical standpoint, not from the pure standpoint of what these 4 assumptions were. But do you remember back in the lab when we applied Bernoulli's equation? I'm sure you remember. The Venturi experiment. We did the Venturi experiment where we had a pipe, and on the inside of the pipe there's a section that has a throat. And what we observed with that experiment, with a series of piezometers that were tapped in, we watched the pressure in the system start off high and decrease and then go back up again. And why did the piezometric pressure decrease? Is because the velocity increased through the throat section. Velocity goes up, pressure goes down. Now, why could we apply Bernoulli's equation in this case of the Venturi? Is because we weren't going any great distance. These weren't too far apart. And so friction losses in that pipe were pretty minor. There's not going to be a lot of frictional loss when the tubes are so closely spaced. But over a really long distance, say the distance from a water tower to your house, there's going to be a lot of friction loss. We're not talking about inches anymore. We may be speaking about miles. And so that steady loss of pressure due to friction of the water and the pipe wall interaction is far more significant. So we have to have an equation that builds on the principles of Bernoulli but accounts for some other things along the way. And that's what the energy equation does. You'll notice it has many of the same terms that Bernoulli's equation had. Here is pressure head. Again, has units of meters, just like the Bernoulli's equation had units of meters. Now here's the velocity head term, but there's some differences. If you look, now there's this alpha factor that's in front of the velocity head term, and then there's a bar above V. We've spoken about the bar above V. Does anybody remember what that symbol indicates? Average, right. And so when we were using Bernoulli's equation, we weren't talking about average. We were talking about applying Bernoulli's equation at a single point. And so if we had some pipe, for example, and applied Bernoulli's equation, we were talking about here's location 1. It's a point. We don't have to calculate the average velocity because we're talking about a velocity at one tiny little point in space. But when we apply the energy equation, we're not talking about the velocity at a point. We're talking about what's the velocity on average across a section. And so there's a location. So 1 is like a line instead of a point. And so we want to know the average velocity across the entire cross-section at our point of, at our location of interest. And so that's why V has a bar above it, average velocity. Now the alpha is a little bit more complicated, and I've got a slide here in a minute that talks about what it is, but the name of that term is kinetic energy correction factor. And it accounts for the fact that we have velocity profiles. And let me draw the typical shape of the velocity profile for laminar conditions. Okay, who can explain like the bullet shape, what it's all about? Exactly. So where is the friction being applied? We all know that there's friction, that the pipe is pushing on the water. The pipe is pushing at the water where the pipe is. And the water that's furthest away from the edge of the pipe can flow the fastest. And so here we've got high velocity at the center, a little bit lower velocity as you get off the center line, and then edge of the pipe, the velocity is moving quite slow. So this profile means that when we square the velocity at a certain location, we're going to be coming up with a mathematical error that has to do with the fact that the velocity up here is much greater than the velocity down here, and when you account for the average velocity, you need to boost the overall factor up a little bit because some of the velocity at the center of the pipe was higher than we really gave it credit for. In other words, if you just use the average velocity, you're sort of shortchanging how much kinetic energy there really is in the velocity head term. And so alpha is a correction factor to increase how much energy we assign into the velocity head term, because really there's more energy there when we just use the average. That's not accounting for how much extra energy there is at the center of the pipe.
Is alpha based on the type of fluid or the diameter of the pipe?
Good question. Alpha is actually based on your Reynolds number. When you have laminar conditions, you'll use alpha equals 2.0 for RE is less than 2,000. How often does that happen? Taylor's shaking her head. Why? Exactly, yeah. The laminar conditions are rare, and so most of the time what we're more interested in is an alpha of 1.05 for Reynolds number is greater than 2,000. That's not much of a correction factor, is it? We're just adding an extra 5% of kinetic energy into the velocity head term because using the average velocity sort of undercounts how much energy there really is. Sometimes people don't even bother including alpha. So sometimes I may not, in a certain problem, I may say, well, let's just assume alpha is 1.0. But then when we're really trying to nail it and we have confidence in all the other values that we've measured, then maybe we'll go ahead and take the time and putting in the actual alpha is 1.05. You know, when we're wearing our tuxedo and doing a calculation with the top hat on and a monocle, that's when you whip out the 1.05 correction factor. All right. We've got the elevation head term, Z1, means the same thing as it did previously. It's just the, what's the elevation of the pipe section in question. Now, H sub P, there's a lot of things that P could stand for. In this case, it stands for pump. We're going to be applying the energy equation, like I implied earlier, over very long distances. From a water tank, maybe. There's a water tank all the way through the neighborhood to a fire hydrant that's shooting water all over the place. So if this is location 1 and here is location 2, there might be a pump somewhere between there. And the purpose of the pump is to add energy to the system. And in the accounting of 1 and 2, if something is adding energy to the system between 1 and 2, we put that on the left side because flow goes from 1 towards 2. That's a very important part of this equation, is that flow goes from 1 towards 2 by definition. And so because of that definition, you've got some amount of energy at 1 plus how much energy is added by the pump will be equal to however much energy there is at 2, etc. Any questions about a pump? Pump will have the same units as all the other terms have. Our pump head will have units of length.
Isn't there where the pump is on the right?
Good question. No. All it matters is that it's between 1 and 2 in the energy equation. In reality, yeah, it matters because, for example, if we put the pump all the way at the end, then there could be cavitation because, like, maybe the pressure is decreasing as you go through the pipe, because of friction losses. And so if you have the pump at the end of a very long suction side, this would be suction side. If you have too much of a too much length on the suction side, then cavitation can occur. So, I mean, according to the energy equation, we don't see where it is when we're doing this accounting, but in the actual physical placement of it and the real world implications, it does matter. Normally, you'd put the pump as close to the origin as you can. All right, P2 is the pressure head term. Alpha is, again, the kinetic energy correction factor. The velocity head term is just whatever velocity head there is at location 2. And we can pick any 2 locations in the system. It doesn't have to be here at the surface of the reservoir. Why do you think that a lot of the time I'd choose this as my location 1? Because I know lots of things about it. I'll know the pressure there, and I'll probably know what the elevation of the water is there. That would be an advantageous place because the velocity head will be 0. If it's just water sitting in a tank, it's not moving. So I can cancel out a lot of terms. But the energy equation applies in any 2 points in the system. I could let this be location 1, and that could be location 2, and it's valid anywhere in the system. But sometimes I'll just choose places that allow me to cancel out more terms. Okay, P standard for pump. Any guesses on what T stands for? Similar to a pump, but backwards. Turbine, exactly. And so a turbine takes energy out of the system in order to generate electricity. It's sort of, instead of putting electrical power in, and in the case of a pump, what you're doing is you're taking electricity, spinning a motor. The motor is connected to the pump, and the pump is got like an impeller on it. It looks like the propeller of a boat. And that spinning propeller is actually adding pressure to the fluid, and then because more pressure has been added, it can flow more quickly. That's what a pump does. A turbine does the opposite. It uses the flowing water to spin the impeller. That spinning impeller is connected to a generator, which is just like an electrical motor in reverse, and the generator sends electricity out. And so T is turbine, and it's intentionally on the right-hand side of the equation because between 1 and 2, what we're saying is that there's a turbine somewhere between 1 and 2, and that turbine is taking energy out. And so if you say the energy at 1 equals the energy at 2, except for what if you add energy through a pump or take away energy due to a turbine, or this last one, H sub L, stands for head losses. And that's where we put pipe friction and local losses, H sub L. So it's an accounting process where the energy, and by which I mean the pressure head, velocity head, and elevation head, those are the three terms, those are the three places the energy is stored. Energy is stored as pressure, elevation, or kinetic energy, which is the velocity head term. So we've got some amount of energy at 1, and then in the flow moving from 1 towards 2, energy can be added or taken away. If energy is added, it's on the left-hand side, and energy is added as a pump. And if energy is taken away as losses or as a turbine, it's on the right-hand side of the equation. This will make sense when we get some concrete calculation examples here in a minute. Before we move on, are there any questions about this slide? Yeah.
The H's been given to you like a weird amount.
Oh yeah.
Typically just a number.
Weird as you could imagine. Yeah. Normally, like the pump head, maybe instead of giving you the pump head directly, we'd say that there is a pump spinning at a certain number of RPMs, and you'd have to go look up what the pump head is out of a table. Or maybe instead of telling you how much head is taken out by the turbine, we would do something similar where we would say that we'd use the power equation. And we'll look at the power equation, but it's a function of the flow rate, the elevation difference between the in and the out of a reservoir. So it won't always just be a number that's given directly. Sometimes you'll have to calculate it. But H sub L is the most complicated of all to calculate. And we'll spend like the first 2 weeks of hydraulic engineering getting the really accurate way of calculating head loss. You know, when we're using water gems, one of the first things you do is you switch it from Hazen-Williams equation to Darcy-Weisbach. And Darcy-Weisbach is the most accurate equation you can use for calculating friction losses due to pipe friction. And so that's what we'll be doing in hydraulic engineering, is finding like the real state-of-the-art way to calculate head loss. And it's time consuming, but we've got the time, so we'll consume it next semester, not this semester. So here it is, the energy equation again, along with each of the definitions. Head loss has two components. The local losses, which is what we'll be looking at in the lab in December. We'll be looking at bends in the pipe, sharp bends and gradual bends, and we'll see if one of them causes more head loss than the other. We'll be looking at different types of valves, like a gate valve versus a globe valve versus a butterfly valve, and try and see how differences in valve types lead to maybe more energy being lost versus less. And expansions, like when a pipe goes from a small pipe towards a large pipe. How is there energy loss in an expansion or a contraction? So those are called local losses. Sometimes they're referred to pejoratively as minor losses, as though they don't matter that much. But it's relative. Usually these local losses are minor if you have a few valves and then a really long pipe. If that's what you've got, a handful of these fittings and then a really long pipe, then maybe there'll be 2% of the friction losses. But in the pipe rack, when you've got a relatively short pipe and a lot of valves, then they're not minor anymore. So I like to refer to them instead of minor losses as local losses. And what local means is that the energy is lost at a point instead of over the entire length of a pipe. So the energy loss is localized to a single feature inducing turbulence in the flow. And that's what each of these does, is it causes some sort of a turbulent disturbance of the flow that makes energy be lost. So here's showing a long pipeline. I think this is the Trans-Alaskan pipeline that takes oil from the North Slope all the way to Prudhoe Bay. A very, very long pipeline. Lots of pumps along the way. Now here's...
Quick question about the head loss. Is that like a summation of the head losses, or is there
Yeah.
only one?
It would be, H sub L means both the local losses and the friction losses.
So you can have two.
I'll show you. HL is H naught plus HF. These are the local, and these are the friction. And so in a pipeline, you could have both. If we had this situation, and we put in a couple elbow valves along the way, uh-oh. Here we go. Fire the contractor. All right, there we go. So here we'd have a local loss here and a local loss there, and maybe if we put in a valve here, there'd be a local loss there, and then also there would be frictional losses. So there can be both frictional and minor, oops, did I say it? Local losses in the same system. Local and frictional can coexist, yeah. All right, so here's how you calculate the alpha. If you know the ratio of the average velocity to the velocity at a point, and you integrate over the cross-sectional area, the incremental cross-sectional area, and so dA is simply the circumference, and there's some incremental area as you step through increasingly large rings of the diameter of the pipe. Ultimately, if you integrate that for laminar flow, when you have a parabolic shape of the velocity profile, you'll get that alpha is 2. And you don't go through exactly the same process when conditions are turbulent, because remember, turbulent flow has a lot of irregularities in the velocity profile, and it's changing at any particular instant. But it's approximately 1.05 for any flow conditions that are turbulent. So this is the type of problems that maybe we'd apply the energy equation to if we had an elevated reservoir and we wanted to find out how much electricity could be extracted from a pump station, from a power station located at the base of that dam. So we've got some pipe connecting the upper reservoir and the lower water, a penstock, and through that penstock there's going to be energy loss because there's frictional contact between the water and the channel. We'll have a change in elevation. You notice that both of the elevations are listed there. So in this case, there's a pretty dramatic 600-meter change in elevation. And the energy equation will allow us to find out the amount of electricity in terms of watts that could be generated from a situation like this. We'd have to know the flow rate. We'd have to know the elevation difference. And we'd have to know how much energy is being lost as the flow goes through the pipe. So here's the first example that will work. We're taking a look at a case where two pipes are, a pipe is connecting two tanks, and the water surface elevation is known for both of the tanks. And we want to know what is the flow rate, and what's given is how the head losses vary. You'll notice here there's an expression that tells us how to define H sub L. All right. So this kind of an equation here, it says the head loss is going to be defined as 0.04 times the length of the pipe times the velocity squared divided by 2g. And the reason for that is that, next semester when we really get down into it, we're going to calculate the head loss due to the we're going to use the Darcy-Weisbach equation for that. And that is head loss is FLV squared divided by D2G. So what I'm doing in this example is I'm saying let's combine the diameter and the friction factor together, and let's just say, for sake of illustration in this problem, that those two together are 0.04. And so what we're trying to say is that the energy loss increases with length, and it makes sense that it would be length to the 1 power, because head loss accumulates in a linear fashion. If you have 2 meters of pipe, you're going to lose twice as much energy as you did if you only had 1 meter of pipe. But you'll notice that velocity is squared. And so what that means is that if you have twice the flow rate going through a pipe, you're going to lose 4 times as much head due to pipe friction. And that's the reality of the energy loss due to pipe friction. So let's just plug some of the known values in here and find out if we can predict what the flow rate is going to be between these two tanks. Okay, so we're applying the energy equation, which says that we've got a pressure head term, alpha 1 V1 squared divided by 2G. The velocity head term for 1, elevation at 1, pump head, pressure head at 2, kinetic energy correction factor at 2, velocity at 2 squared divided by 2G. Elevation head, turbine head, and head loss. All right. The most logical place for us to select as location 1 and location 2 are the water elevations in the respective tanks. And so this would be 1 and this would be 2, where the water is at. And we know that the water elevation here, water elevation is 200 meters. The water elevation here is 190 meters. So the pressure at 1 will be 0. The pressure at 2 will be 0. The water inside the tank isn't moving. The water through the pipe is moving, but we're going to assume that the tanks are so big that it's not like the water level is dropping really fast. It's a pretty big tank, and maybe the water level slowly decreasing, but it's so minor, we're going to ignore both of the velocity terms. There isn't any pump between the two pipes, nor is there a turbine between them. So all we've got is a change in elevations and the equation we're going to use to characterize head loss. And so Z1 was 200 meters, Z2 was 190 meters, and then the head loss is 0.04 L V squared divided by 2G. Okay, so the difference in elevation between the 2 points is 10 meters, and we can substitute in the known values. It's 200 meters of pipe length between the two reservoirs. It says through 200 meters of 350 millimeter diameter pipe. Okay. The velocity through the pipe isn't known, divided by 2G, meters per second squared. So we can move the 2G over to the left-hand side, divide by 0.04, and divide by 200, find the square root. The velocity is 4.95 meters per second. Before we go any further, let's try and make physical sense out of what's happening. What if the pipe was longer than it is now? What effect would that have on velocity, on the velocity of water going through the pipe? What if it was 400 meters instead of 200 meters? Would the velocity be higher or lower than it is now? Lower. Why would water move at a slower velocity through the pipe if the pipe's longer? more friction, and so there's not going to be as much of a driving force relative to the friction losses. You have to think about, like, why is water going between these two tanks? What's pushing it from 1 to 2? What's the extra elevation? This is the driving force. The driving force is how much higher the water level is at tank 1 compared to tank 2. And if that driving force is small compared to the resistance, the resistance is how long the pipe is and that conduit that it has to travel through. The flow rate will decrease if there's more resistance. And so a longer pipe would give more resistance, or if the pipe was more rough. I told you about the Darcy-Weisbach equation. This 0.04 is reflecting how rough the pipe is, and maybe it turned out that the pipe is made out of jagged, rusty material and it's very rough. That would increase the friction factor, and again, that would decrease the flow rate. So we've got the velocity. We can find the flow rate simply by applying the continuity equation, Q equals VA. So that's 4.95 meters per second times the cross-sectional area, pi 0.35 meters squared. Divided by 4. So that's 0.476 cubic meters per second, where that cross-sectional area is 0.09621 square meters. If you connect, excuse me, if you connect a hose to a barrel, you can calculate the flow rate that should come out of the hose using this energy equation. You'd need to estimate what the friction losses are going to be in the hose, but it's a very useful idea that friction loss accounting allows us to estimate what the flow rate will be. Now here's the same figure, but we've changed things around a little bit. Now we know that along the pipe there are a pair of pressure gauges. They're 145 feet apart. The pipe is horizontal, and the measured pressure difference is 25 psi. So what's the head loss between those 2 points? All right, why don't you work on that with a partner? See if you can calculate the head loss by knowing the change in pressure. So you pick 2 points in the pipeline and apply the energy equation between them. You've done this in the lab before. We've got water flowing horizontally through the pipe. We're just concerned with this section that's 145 feet long. And what we know, the pressure change between the 2 points is 25 psi. If we multiply by 144, which is how many square inches there are in a square foot, that gives us that there's 3,600 pounds per square foot. Okay, between point 1 and point 2, we can cancel out the velocity head terms because the velocity is the same at 1 and 2. The pipe diameter isn't changing, and so velocity head at 1 will equal the velocity head at 2. Even though pressure is being lost, the water's not slowing down. And sometimes that's a hard concept to grasp, that, if it's losing energy, it seems like the flow would be slowing down. But what we know mentally is that since it's in an enclosed pipe, it can't slow down because the water behind it is pushing it forward. There'd be no place for it to go if it was slowing down. A pipe can't allow accumulation of flow. And so the flow continues at the same rate in the entire pipe, even though pressure is decreasing. The energy loss is manifest in the pressure decrease, not in a reduction in velocity. The elevation head is the same at 1 and 2 because it's a horizontal pipe. And so what we end up with, and there's no pump and no turbine. So what we end up with is that the change in pressure is equal to the head loss that's observed. And between these 2 points, there's only pipe friction. There isn't any fittings that are described. So the head loss is the 3,600 pounds per square foot divided by the unit weight of water, which is 62.4 pounds of force, and we were talking about pounds of force, pounds force per cubic foot, 57.7 feet. And what's the significance of that? Well, if we had piezometers connected at the 2 points so that pressure was measured as some elevation rise of water, then the difference in the water elevations would be that 57.7 feet. That's how the pressure head would manifest itself, as the flow is continuing at a consistent flow rate, the velocity isn't changing as friction robs the flow of energy, but pressure is decreasing, and so pressure head is decreasing. It didn't say anything about what the flow rate is, did it? Was there a question? If we wanted to know the rate of energy loss, it would be. And I think in a future example, I ask us to calculate the slope of the energy grade line. And so since we know it's 145 feet apart, what we could do is we could calculate like what's the slope of the line that connects the 2 piezometers. And that's meaningful because sometimes we want to visualize the flow and graph it out. Like when you're designing a water treatment plant, you have all the drawings of the pipes and drawings of where the tanks are. But you also do drawings of where's the pressure at every point in the system, because you want to make sure that there's enough energy to get the water from A to B without having pumps everywhere. You want it to flow by gravity. So we'll draw energy grade lines in an in-class activity the week after Thanksgiving. All right, we'll change gears a little bit and talk about some of the things we need to know before we can calculate the power capacity of moving water. Excuse me. There's a definition that's in your text of flow work. And let's consider this figure here and see what we've got. We've got a control volume that is the dashed line at time t. The water inside of the control volume is the system. Remember that a system is a continually connected stream of particles. So inside this pipe element that has a changing diameter, we've got a certain amount of flow that's moving towards the right. And in a time increment at t plus delta t, the control volume changed. This control volume is continually enclosing a certain number of particles. The system is moving, and so we can move the control volume if we want to. There is pressure inside of the pipe, and so on the outside of the control surfaces, the pressure is pushing on the system, and if we consider the cross-sectional area and the pressure that's acting on it, that's as though it's an external force. And so you know that force is pressure times area. So it's like there's a force pushing this way, and there's also a force pushing that way on the control volume. The flow work is the amount of work required to move the flow over time. And the little dot on the top there is talking about not only the work, but the work per unit time. The definition of work is force times length. So we said that there's a force. If you look at the pressure that's pushing on the control volume, there's a force here and there's a force there. Now what is the length in the work term? The length is how far it's moved in a certain amount of time. So in 1 second, maybe the control surface has moved a few centimeters. And so we've got some change in length. And since there's a time unit there, then that turns work into work flow. In the same way that we had mass flow, you know, m dot was talking about mass per time. W dot is talking about work per time. Since the velocity of movement is a length per time, then this is the way that we can calculate flow work. It's how much work is required to move water through the pipe over time. As you'd expect, the amount of work increases with the friction of the pipe or with the velocity of the flow. If we want to find the difference in work between 2 points, we can do that by accounting for the change in pressure between 2 and 1. Now the velocities would be the same, but the direction of the velocity is different because, well, for one thing, it's the pressure is pushing to the left at location 2, and the pressure of the surrounding fluid is pushing to the right at location 1. And so we can go through this process of finding the workflow over time. And what do you suppose are the units of that? What are the units of W dot? Well, let's find what are the units of the things that are used to calculate W dot. Okay. W dot has units of pressure is going to be what? Newtons per meter squared. That's what pressure is. Velocity is meters per second, and area is meters squared. And so those will cancel out. Workflow is Newton meter per second. So that's the units of flow work. Newton meter per second. Shaft work is taking into account the work that's done either on the flow by a pump or by the flow on a turbine. And this is kind of another one of those cases where you have to read word statements and find out if we're talking about, is it that some device is doing work on the system, like a pump does work on the system because a pump is adding energy to the water, but a turbine, instead of adding energy, a turbine takes energy. And so a turbine would be done by the flow. And so a turbine decreases the energy in the system, where the system is these continually connected number of water molecules, whereas a pump increases the energy of the system by adding pressure. And so the work is negative in the case of a pump. It's removing energy. But the work done is positive for a turbine. The work is negative because it's the pump is not removing energy from a system, but rather it's adding energy to a system. And this steady flow energy equation shows that if we have heat transfer, that can be accounted for with Q dot. And I think some of you have probably taken thermodynamics, and maybe some of you are going to be taking it next semester. But if you want to take consideration of all of the energy in a system as water is flowing between points, you take into account the change in temperature between the 2 points, so the flow of heat, and then also the work change between 2 locations. And you can apply the Reynolds transport theorem, which says that if you enclose a system with control surfaces, you can keep track of the flow out and the flow in, and the difference between the workflow out and the workflow in will be the workflow that's accumulated in a system. And here we've assumed that there is no long-term energy accumulation in the system. And so there must be an increase in temperature. In a pipe network, the water temperature actually does increase because of pipe friction. You know, we're talking about how all this electricity has to be used to move water from one place to another. There's pipe friction, and just like if you rub your feet on the ground and then fill your shoe, it's warmed up a little bit, or rub your hands together. The reason why they get warm when you rub them together is because of friction. Now, friction generates heat, and the same thing is true with flowing fluids, and so it's perfectly appropriate for us to keep track of heat transfer to the system because of the energy losses goes into heat. Now, it's almost immeasurable. You know, the temperature increases in a pipeline may be just a single degree at most, but still there is a measurable difference in temperature. And so there are a couple of terms that are sometimes used interchangeably, and the last thing we're going to do today is just revisit the vocabulary of these terms. Energy has units of joules, or when we're measuring energy in terms of the energy equation, it has units of meters when we're dividing each of the terms by gamma. That's different from work because energy is used to perform work, and the units of work are also units of joules, but we differentiate between energy and work in terms of the vocabulary. The way that they're used is just the work is what gets done, and the energy is what's consumed to do the work. And finally, power is when we add an element of time dependency into either of the two. When we're measuring how much work is being done per time, or how much energy is being expended per time, that's power. The power equation that we'll use in either pumps or turbines is shown here. Power is the flow rate times the unit weight of the fluid times the pump head, and this is the pump power equation. We could write a turbine power equation just by substituting in H sub T instead of H sub P. Now this is not accounting for anything related to efficiency. You know, pumps and turbines are never 100% efficient, but if they were, this is the power equation. And when we get together in class on Tuesday after Thanksgiving, we're going to apply the power equation and do some calculations to find out how much electricity do we have to add to a pump to move water from place to place, or how much electricity could be generated by a turbine. So that is it for today. Let's just revisit these announcements one final time. It's going to be a while since we see each other again, so burn it into your memory.
Will we be able to do any of the homework tomorrow?
Yeah, you can get started on the homework. The lab assignment will be due on Tuesday the 3rd. The homework assignment will be due on Thursday the 5th. And you know, we're doing a lab on Tuesday the 3rd, but you won't have a report for that. So it'll just be, you'll do calculations in lab, and there won't be anything for you to work on outside of lab. So really the only other things I'm getting from you is you're going to turn in that lab on Tuesday, turn in the homework on Thursday, and then we'll have a final exam. Do you want a quiz? Is that a good thing or a bad thing? All right. We'll have no more quizzes. All right. Okay. Have a good break.